All right, so let's start. From our previous discussion on Thursday or so, we talked about batch reactors. So we talked about three different processes: normal batch reactor, semi-batch reactor, and then we looked at batch distillation column. So we moved how to model continuous reactor. Look at the normal CSTR, uh, normal CSTR, normal CSTR. Then we'll look at CSTR with what constant holder. For that, we'll look at CSTR with varying holder, and then we'll look at gas phase pressure CSTR. Yeah. All right. So let's and then we'll look at scenario, and we'll try to develop the mass and then the energy balance equations that surrounds each reactor. So let's look at the normal CST. Normal CSTR. This is what we call a continuous reactor, or we normally call it what? Reactor. So it's usually a tank which has a continuous flow of reactors into it with a certain steering mechanism to allow a reaction to take place. The reactants flow out continuously. Usually in this reactor, you have something like this. You have something, then you have the in, then you have an, and this one moves continuously. Once it's coming in, it's also going out. So product out. The continuous system. The CSTR normally we normally say it runs on steady state. Steady state means that there's no accumulation. Whatever that is coming in leaves. But sometimes you have a dynamic one when it comes to changes in the level in the tank. So it means that there have to be some time to allow accumulation before the product moves out. That is more like um, a dynamic process. But the normal one where there's movement, I mean, a product in, reactant in, and product out. Normally assume is main features of this type of reactors is that ensures a uniform concentration and then temperature distribution, the steering mechanism. You always have be able to achieve constant uh, concentration and temperature, or you see that the variation in temperature and concentration quite real. Another thing is the concentration and temperature of the materials leaving the tank really should be exactly the same as those that are coming into. So we ensure that the material balance and the energy balance. If CSCRs are actually widely in large scale production, unlike the batch. Remember, in a batch process, we use it for small production system where we are so much cautious about the kind of reaction. Mostly to reactions here are very, very slow. Hold on, I'm coming. Yes, guys, sorry. I think I was. Let's continue. So, as I was saying, unlike the batch reactor, this one is used in large scale production, and usually this one takes place in where reactions are very fast. If the reaction is slow, it's better you use a batch reactor where you can monitor the reaction very, very, very well. So compared to a batch processing, continuous operations result in what? More consistent product property. And really the energy balance is well managed. Okay, so let's continue with this. So because of that, to ensure a good operation of a CSTR is very much necessary for us to understand its dynamic. And I think this applies to almost every unit operation. If you don't get the characteristics very well, it becomes difficult to write the equations that can govern its behavior. So you must always try to get the realistic perspective of the equipment so that you compare it to the practical one you are dealing with. So if there's a problem, you be able to diagnose the problem. And mostly this is what happens in industry. That's why we always want to have a theoretical background of any software you are using. Because if you have the practical background, when you now use the software and you identify issues, the goal is to go down to the variables and see which variable is causing the changes you are seeing in the, I say, the industry perspective so that you can diagnose it very, very well. So in this course, we're going to consider very simple CSTR. That's the first CSTR we have. We're going to consider that one. And then we see how we can model it. So first, like we do every time, we first have to understand what the dynamics of the system. When we are done with that, then we go ahead and we deal with the model, drive the equation. So let's look at this and let's describe this process. Let's assume that you have this simple CSTR um, equipment here. So let me come to it. So we have this CSTR. We have the stirrer here. This is the stirrer. This is the stirrer, right? Then you have your product coming in here, this A, and then it's coming out here as what? The output. This is the output. And then when it comes in here, there's a reaction here, and this stirrer ensures constant what? Distribution, temperature, and also it also provides what we call the necessary agitation for the reaction to take place. And we are assuming that it is what? First order reaction. So because of that, you're having A coming in, then it's going to form B, then B flows out. of the reactor. Then because of this reaction, the reaction is exothermic. And if it is exothermic, what happens is that you have this cooling or heating system here that takes away, or that adds heat to the system to ensure that the reactor operates at the required temperature. So if you consider this, what are we going to have for our mass balance? You're going to have what? The accumulation term here. This is the accumulation, right? Then you have the input, you have the output, and then we have this term here is the now source, or what we normally say the fuel. You remember? Now, there's also another thing. Because there's a reaction here, there will be what? A reaction mass inside the system. So, for example, if I want to check the total energy balance, then I'm going to look at what? Accumulation, input, output. I'm looking at the component. I'll look at the input component, accumulation of the component, um, the generation of the component, and then the output. So we have four terms for that. If it's the energy balance, you have energy inside, temperature in the reactor, then the accumulation temperature, then the Q here, the additional heat you are putting, then the input heat, and then the output. So that's how we're going to or drive the energy balance equation. So let's go to the next slide. I appreciate. So we still have to specify what our assumptions, if you remember. We must specify our assumptions. So for the assumptions, before we come to that, you're saying that we have an existing stream, right? Which contains a mixture of both reactants inside here. The product is B. This B is withdrawn out here. So B is withdrawn out. Okay. Then B is withdrawn out. The reactor is withdrawn from the reactor continuously. The volume flow rate of FO, and that's this. You can see it here. Then it comes out with a composition of what? CA, then a certain temperature. Now, to remove the exothermic heat that is generated due to the reaction, we have the cooling jacket surrounding the reactor. Now, you see that this jacket we have here is just used to remove the heat that is formed inside. So it's a cooling system. So instead of putting hot steam or something, you rather put a cold water, compensate the exothermic reaction that is forming. So in this context, heat is what blocks from the system here to this. So there's a movement of heat in the system here. So let's look at how we can write the mass balance equation for this. Assumptions we have is what the heat loss from the process, what negligible, which means that we are assuming that the insulation is perfect. Then also the mixture density and the heat capacities, we assume that they are constant. And the coolant is perfectly mixed. Therefore, the temperature everywhere in the jacket, the mass of the metal wall is negligible. So the thermal inertia or the movement of heat is what constant. We are also assuming that there's a good there's a good assumption for the heat capacity of the steel. Okay, that of the steel, which is an order of magnitude of water. If you know the specific capacity of water, I think it's stated here as 0.1 BTU per pound per Fahrenheit. Then we are also assuming what there's no spatial distribution of concentration and temperature. means that we're not going to apply um, Taylor series or Taylor expansion here. So we're just looking at the LAM parametric model, changes of concentration and temperature, but with time, no distance or no spatial. Right. Next assumption is that we assume that the exit stream has the same concentration and temperature as the entire reactor liquid. And then the overall heat transfer coefficient is assumed constant, which is the Newton or the heat transfer coefficient, if you remember. We are also assuming that there is no energy balance around the jacket. Consider that anything around the jacket, because there's no movement around, assuming it is what constant. So I'm not going to do balance. Sometimes in some reactors, you will have to do energy balance around the reactor. And that has to do with also trying to find the changes in the temperature of the coolant you are using. So you have to also write a mass balance equation for the coolant, know the temperature. Especially if you feel the temperature in the coolant is very important or it can cause a problem, then you need to also model it. It doesn't go too much to affect your reactor. Then also we assume that the reactor is what? It's a flat bottom vertical cylinder. So with this, we are able to calculate the mass transfer or the heat transfer area around the jacket. So having done that, the next thing is to write the continuity. So like I said, we have the reactor this way. We have an input. We have an output, right? Input here. Then we have our accumulation terms. So there's a certain what? Volume here, certain density, right? And then there's a reaction. So what we normally do, we write both the terms. So accumulation is what? That's inside here. So accumulation will be V, um, let me make it. Accumulation will be change in accumulation will change in mass. We got what? Input. Input mass. That's the rate, right? Let me say rate input mass minus rate of output mass. We know that this one here is equal to rho v. Mass is equal to rho v. So same as this. And this one, we now write for this. The input is coming at a certain flow rate and a certain concentration, at a certain density. So here, the mass is going to be the flow rate times the density, because this flow rate here is measured in what? You get it? Then the output also will come with an output flow rate, certain density. You get it? So once you establish, you now equate them. For a steady state, we know that the accumulation term is going to be zero. Accumulation term is zero. It means that your output here will be equal to your input. If it is a normal dynamic, then you need to have accumulation. After we have stated them, so you see that this is our accumulation. And we further break the V to what? Area times H. So in this reactor, like I do, is the height that determines the volume. Look at it. So area is so constant, right? So it's the height that determines. So more particular about predicting the changes in the height of the volume. Once the height of the volume changes, we know how much mass is accumulating inside the reactor. So when we have this, the next thing is just to apply the terms, right? So from here, just this one is equal to this. So that's what you can see. Have it here. That's what we have. Okay. Now, I can further break this one down. In a CSTR, if you remember when we talked about variables, the output variable is sometimes also known as a manipulating variable. So the output variable is usually controlled by the valve at the output end. Each valve has its own equation related to output outline. That's the flow rate outside. Because the amount we are flowing out is controlled by the valve. I have this. You have a valve here. The FO is controlled by the equation of this valve. Okay. So in this perspectives, for a normal CST, I would believe that the control valve, the flow rate, the flow out FO is related to the volume of the reactor. And this is further given for this kind of CSTR as equal to root of NACH experimental. Okay, so now adapt this in our calculation. You also remember that we assume that density was constant. Density is constant from our normal accumulation. We said the what? The ACH on T is equal to I because density is constant, right? Equal to Fi minus get it. And now we are saying FO is equal to this. We are going to have um, ACH on the T equal to Fi minus root of 10 ACH. Get it? So with this, you divide through by what? ACH. So if you divide through by, if you multiply this by 1 over AC, cancel. This will be AC. This will be AC. So when you break this down, you get this equation. So therefore, the changes in height in the reactor is controlled by the input over the area minus this thing. So that's the material balance equation for the CST and not the component total, which we call the TC reactor. After this, we go straight to the component analysis. After you have the total, component analysis. So let's look at the component analysis and see how that one takes effect. For the component analysis, we start with the first component. The reaction was A to B. We want to monitor both these. So we're going to have the inputs. That's the same way. Same way. You have this. You're going to have A initial, then A calculated, and then A generated. The accumulation of A is going to what? If you remember this one, that's the moles of A, and the moles is equal to what? Volume times concentration. It's going to be VCA. You get it? Should be equal to input moles of A. We are flowing moles, so it's going to be the flow rate, the initial concentration of A minus the output, right? It's going to be this. Then plus or minus, you remember RA to bracket V. Remember that, and this one will be the reaction M. So if A, from our reaction, we are having A to B. So A is being depleted, so it's going to be minus. So here it should be minus. So we just replace this term by the reaction to B. So it's going to what? A, C, A. This by this. Then your continuity that. So that's what you have here. So you can see that you have it here. This way. Now, in this CSTR, you know that the volume changes with respect to what height. If you remember, concentration also changes with respect to the reaction. So because of that, we have to use the chain rule to break this down. So when you apply chain rule, no chain rule, we hold the V constant, we the concentration, the time, as hold the concentration, you differentiate the volume with time. You equate it minus the output minus the rate of A area in the system. So once you have that, it becomes easy to make. Now, when you have this, if you remember, let me go back here. From the total continuity equation, this one, yes, you can see this total continuity equation. We had the V is equal to F1 minus Fo, right? So we'll now come here. The same term is here, obviously, the V. We had the V dt Fi minus F. So we'll replace this here. So we now have Ca Fi minus Fo plus V Ca over dt is equal to Fi Cf minus Fo Ca minus Ra. Then you now make this the sum. That gives you the quantity. So when you do that, you're going to have this equation for the CCE. That's the component continuity equation for A. And we know that this reaction here is equal to this. So you replace it. After that, you can even change this A to Arrhenius equation. Then you have your so that is the equation here. You can substitute it into the main equation. You have your component continuity equation for A. I'll write this for B, but in B, B is going to be positive. So this term here will be plus for B. Have that for a normal. Yeah. After that, you go to the energy balance for the CST. For the energy, it's the same way as the mass. Like I told you, energy. This is the CST. You remember, we have something coming in, something is going out, right? Then we have accumulation, we have generation, and also we have the jacket, which is Q. There was a stirrer in it. If you want to add the stirrer, that's the work done. That's W. Remember, but in this case, negligible. So this is not there. So we need to have how many terms? I think 5, right? We have to have 1 here, 2, 3, 4. Equal to. So the same way, come and say MH. Remember our first equation. Equal to what? MH for input minus MH for output plus or minus heat of reaction. Remember this heat of reaction RV, then plus or minus, then plus Q, because this Q is taking heat, then plus W. Remember that, but W is 0, so it's not be there. So we're going to have 1, 2, 3, 4, 5 terms. So you can see it here. So this is the accumulation, right? With respect to temperature, because this is wrote the equation as mh, right? Mh over dt. So m is 0, and then h is Cp delta T. So this is the input term, this is the output term, this is the energy from the jacket, this is the energy from the reaction of this. You just have to area. So we know they said it's a flat bottom flat, so the area will very soon specified. I'll show you how to calculate after that. So once you have this, you go forward to divide through by what? V rho Cp. We want to make what? T over this. When you have that, you're going to get the total equation, total energy balance equation. You can go over it and see. This is the input and output term. This is due to the reactor. And that's coming. Then this is, so you can now use this to calculate the inside the reactor at each particular point. The main problem is now AC, which we say the AC is equal to this, because AC goes around the whole reactor. Look at it's like a jacket. So you have this part here, then you have the surrounding of the wall. That's why you have this. This is for this. This is for the surrounding of the wall. That's how you check it. But if the cooling is only on the flat surface here, then you can use this. So you define the area based on the section where the heating jacket covers. All right. So we move on to the next, which is thermal constant hold-up. We're looking at a CSTR that has thermal hold-up. Let's look at how to model this. This system is also very interesting, straightforward, very simple. So it's just similar to the other one, but you see, this one we have continuous reactors together. Our CSTR, but we want to maintain the volume in the CSTR. So let's see how this system is modeled. Then we can nice equation. This we have a simple CSTR under consideration, and the goal here is similar to the previous one. What we're trying to do is you have A flowing here and it's coming out here as product B. We're trying to take it off. So in each reactor, reaction keeps going on. So A will come here first, react first. Now, series reactors this way are used when one stage that it's not enough to complete the reaction. So you move it, the first one reacts when the reaction is, when the process is limited by the rate of reaction, move it to the second one, continue the process, move to the third one, continue the, all these are all converting A into, the reaction could be different, and I think we know how to write the rate of the reaction. So just like the first one, in this system also, we assume that what temperature, the whole that volume of the tray can be different, which means that it can be different temperature here. They can also be and but for this case, the second one is what we consider. For this case, we assume that volume constant. So V1 is equal to V2 equal to V3. T1 is equal to T2. So now let's look at how to write balance equation. Okay. Ideally, you are supposed to write both total continuity equation for reactor 1, component equation for reactor 1. You come here, reactor 2, write the total component, write the component continuity equation for all of them. You have to do how we go. Quite simple. So with this one, remember accumulation. If you take the first reactor, we're going to have what? The changes in volume. Okay. The T equal to what? Fi minus Fo. We are saying that if the density is the same, they'll cancel out. So this is correct. If they're not the same, then you have to bring the density. If they're the same, correct. Now, what's happening is that at this point, whatever that is coming in here is the same thing that is coming out here. So Fo will be equal to F1. And if I put F, because the volume is the same, whatever I put here, F1, so for second reactor, the input is what? F1, and the output is F2. The third reactor, F2 is equal to F3. You get it? So if we do that, it means that Fo is equal to F1 is equal to F2 is equal to F3. The truth is that if this is not true, you can't have constant volume throughout the tanks. Okay. When this is established, it becomes easy to write that for the mass balance, the continuity, we're going to have what? All the F's to be equal to 1. And if that happens, we drive it from here. It means there's no accumulation. This is 0, right? So if accumulation is 0, you have Fo is equal to F. You have O minus F1 is equal to 0. So it means O is equal to F1. So that's why we do that. That's the continuity equation for all the tanks. So for all the tanks, the first tank it will be Fo is equal to F1. Second tank will be F1 is equal to F2. Third tank, F2 is equal to F3. You have this for that. And you go ahead and then establish your continuity equations. Continuity equation with the first term. Remember, so if you have this, you have inputs, outputs, and we have accumulation, generation. So we need to have 4 different equations for each of them. So the first one is what? Accumulation of inside this reactor. So it's going to be A delta. It's equal to what? Input of mole. That's here. So the input minus output. This one here is the same as A one, right? It's equal to, and the input is what? Here it comes in at a certain flow rate of O, then at a certain concentration of, you remember that. So the input is going to be FOC. That's the initial. Then the output, remember the output should be F1. output should be 1 CA1. But we said FO is equal to F1, so this is also, that's why we factorize. So this is both what? Input and out. Then this one becomes the reactor S order. Change this K with the Arrhenius equation. Because F1 is equal to F2, equal to F3, equal to F, can generate the term for. Also write this for B. You're writing this for B, then this becomes, all this become. But you know, if you're writing for B also, you don't have B at the beginning. Let me go. We don't have B here. So there wouldn't be what? E, especially for the first reactor. B will be what? So you can write it. All right. Are you okay? Any question? Can I continue?
So let's continue.
All right. Thank you. The next one is similar to this isothermal constant holdup. That one, we are looking at an isothermal variable holdup CS. So in a isothermal variable CSTR, it's similar to what we have, but in this case, the volumes here are not the same. So it tells us that FO is not equal to F1, which is not equal to F2, which is not equal to F3. They are all different. Because they are different, this we have to write the continuity equation for each reactor. Before this, we need to write the total one. The total is going to be this. Now, so we write total continuity equation for each reactor. Component continuity equation. All right, so we take the first reactor. Considering the first reactor, we have input here, we have output here. So the total continuity equation, this is going to be what? Mass accumulation dt equal to rho input minus, sorry, rho output. The density is this. This one would have been rho v. Density will also. So therefore, you're going to have delta v is equal to 1. So that is the total continuity equation for reactor 1. That will write the component equation for reactor 1. How do we do that? We do the same thing. There's a reaction taking place here, which is A forming B. So the same way, look at the input mass for A. So we are going to look at changes in moles A equal to inputs moles of A minus output moles of A, also minus generation of A. So when you have that, like the previous one, so you're going to have all right, you're going to have what? Remember, this is what concentration times volume. So it's going to be the CA times V1. So you're looking at the to be equal to what? Rho, not rho. It should be equal to F what, right? So it's F naught times CA minus 1. This is going out, it's going to be CA1. Okay. Then it's going to be, it's depleting, so it's going to be minus CA into minus K AV1. So this is component balance for the first reactor. And you do the same thing. You write this for the second reactor, also for the second reactor, the third reactor. So this is the first reactor. This is correct. The second one, we have it here. Second, we have it here. And that's with these equations, now solve and find the concentration of E at any point in time in the reactor. So when you have this, we say that you have modeled that particular reactor. So you know all the variables needed to solve it. You also know all the equations you need to solve the. We're saying that the mathematical model now contains 6 first-order nonlinear differential equations, or what you call, that's what, 3 parameters, or let me say 4. That's what K1, K2, we have N. Then you know the initial conditions. At the initial stage, you know the initial AU. A that will move to all the reactors. We can predict them. We know the volume of the reactor, so we know them. Now, you see that here, V is becoming a variable. Why? Because of the height in each reactor. They are not the same. So the volume in each reactor will be different based on the height for each. And here we say the forcing functions are what? Initial concentration that you put in, and then the initial flow rate. Change these variables, it changes the value amount of A at each particular point. Yeah. All right. So, any question? If there's no question, I'll move to the next CSTR. The last type of CSTR.
Okay, sure. Let's continue.
Okay, boss. So the second, the fourth CSTR, one I try to bring something that has to do with gas, so that we can appreciate both liquid and gaseous systems. Now, for a gaseous system, we are looking at example of what we call a gas phase CSTR equipment. Now, this one has to do with mixing of gases in a reactor. So you have 2 or 3 types of gases. You are mixing them in mixed gas and then use them. And these gases can react with each other. So we are assuming that you have A, and this one reacts to form, A will react to form B, but it's a reversible reaction. So A can form B, B can form back to A. We want to see how to model this kind of reactor. Now, this is a perfect example of that. You see here again that there's a valve here. So this valve will control the amount of this F. This valve here controls the amount of F. Look at the previous CSTR. We said that what the FO was controlled by the valve according to 10 into bracket P. Remember that as in AC. Yes. Now, there's also this kind of valve for this kind of gases will give us a different equation that we use more. So, like we do every time, let's first try to what? Understand the equipment very well. Then we can establish a mathematical equation for the TCE, which is the total continuity, and the component continuity. All right. For this system, we said we have a forward reaction, which is in the order of what 1.5 in A, and the reversible is first order reaction in B. Now, note that the stoichiometric equations are not the same. A and then, so we can't assume A. I think A is 2 and then B is 1. Then the mole fraction, the reactants, the reactor is Y. Why are we using Y? Because it's a gaseous reactor. Mole fraction in gaseous phase is always Y. Mole fraction in liquid phase always assigned by what? X. We also say that the pressure inside the vessel P is absolute. Both pressure and Y can vary at any time. And the volume reactor also constant. We assume that the volume. So the same way we assume an isothermal system also for it. So the temperature is constant. We assume that we are dealing with what perfect gases. So everything that has to do with ideal gas equation can be applied here. The feed stream has a density of what? Rho O, and then the mole fraction YO. Then also we have a volumetric flow rate of FO. That's here. You can see it here. And here, this here reacts. Right. Then also we also have the flow out, like I said, controlled by a valve. And this valve tells us that the flow rate out of the reactor is controlled is at EV, this pressure minus potential pressure on rho. So that's what we're going to. So with the knowledge of this, we have to now apply our continuity principle, which is what accumulation always equal to input. So let's try to find the density, because density also varies in the reactor. Now, you know that from ideal gas equation, we have PV is equal to RT, right? And if this is true, it means that this value here, moles, this molar mass, right? We know that density is equal to mass over volume, right? And then also molar mass is equal to what? Uh, molar mass is equal to N over what? Who can tell us? Sorry,
Mass.
no, come in.
Mass.
Not this one.
Oh.
This is not what I wanted. Sorry. I mean, this. Oh, sorry. This one. Oh, this N is equal to mass over molar mass, right? Exactly.
Yeah.
Okay.
This is equal to mass over molar mass. And then also we know that rho is equal to mass over volume. You have your ideal gas equation as PV equal to nRT. So you can play around with this. So you now have PV is equal to M, capital M, RT, right? So if you have this, you want to do this. So you have MPV is equal to MRT. You do that, you can divide through by what? You can divide here by RT. This will go here. Then you can also divide by, okay, when you divide through by V, this V you cancel this, have this. So you now have M on V is equal to MP, which is equal to rho. You get it? So that's why you have here the rho here is equal to the molar mass pressure over RT. That's this place. Okay. So Based on this, because density is changing, you want to see why density, how density is changing. Because the gases are different, this is the molar mass of one, then one minus, mole fraction should always be equal to one. So the molar mass of the other gas will be equal to one minus the Y. So this one times its molar mass. This time molar mass. So this is what will carry the gas. Pressure of the reactor is constant. This is also constant. Temperature is constant. So it's the molar mass and the mole ratio causing changes in the density of the reactor. So now let's write our continuity equation. So the concentration of the reactor in the equation is going to be established by A to be equal to what? Pressure and then mole. I told you there is a mole fraction here, this Y here, that is causing the changes given the density. That's what affects the concentration inside the reactor. So when you establish, the next thing is to establish the reaction constant. The reaction constant here, for the forward reaction, we had 2A forward and then back, right? B. So the first one is 2A forward to B, right? This one is half. Remember that. So we are going to have K1 is power 1.5 we have here. We are saying this is equal to this, and you can write it in terms of B. And B is what? B comes back as first order reaction. So it's going to be 1 over V. That's why you're because the idea is that in the first word reaction, you are forming B. So this is the reaction, the formation. And in the reverse reaction, you are forming A. So you write it as negative B, right? So you're going to its first order. So you have it this way as B. So when you have this, the next thing is just to write the continuity equation. So we're going to have what? Accumulation in the reactor should be equal to what? Input into the reactor minus output. We know the density M, right? We already said it's affected by the molar mass. That's fine. So when you do this, you can now write the component continuity reactor. So for the component to follow this, so the amount of A, the reactor here, is equal to the input of minus the output of A minus what? Because it's a reversible reaction, right? So this is what? This is the depletion of A. Get it? Plus the formation. So this will be the total reaction. The total equation that can model a particular. So with this, we have what? The two reaction terms here. One is for what? So you see the coefficient here is for the A, right? We're saying that the two that is in the reaction is because of the geometric coefficient. Look at all this. Now you have 5 different equations that can model the system. You have to solve all the 5 equations, of them using Python or MATLAB. So out of this equations, you're going to have volume as a parameter is constant. Constant, you know that, right? The reaction constants are all constant. You can find them in the natural ideal gas equation. Sorry, gas constant is also molecular fractions of each of the gases. So these ones you can find them in it. Then the forcing equation is what? The differential pressure across the system or the system. Here is the density of the gas, initial flow rate of the gas, and the initial concentration of the gas. What we don't know is A in the reactor, density in the reactor, pressure in the reactor, then the flow out. What we're going to do with the system. So you can now tell your degree of freedom. So that is it for the continuous modeling process. I don't know if you have any question. If you don't have a question, we can pause for maybe 5 minutes. Then we finish the last part. So let's come back in 5 minutes time and then we.
Okay, okay, sir.
All right. Thank you. Hello, guys. Can we continue?
Doc, you are here.
Or you are tired?
Yes. Yeah, Doc, can continue. No, you are not. Let's finish up.
Eat. All right. So we'll just discuss some few, I think two more systems. Then we'll. Today should be my last
Okay,
day,
Doc.
right? Today should be my last day, oh?
I thought
Hello?
you said tomorrow. Tomorrow is October
Yeah,
now.
Today my last day or tomorrow?
I think it's tomorrow.
Okay. Can add more things. You guys have time. All right, maybe tomorrow we'll just make it like an open class. We have some. Okay. So in this part, we look at a mass transfer reactor. So we look at a reactor that has mass transfer occurring in that system. For example, you have a liquid and gas. That the gas will absorb the liquid. So there's a transfer of the gas into the liquid from whatever product you want. And sometimes when that happens, you have two things. You have mass transfer limitation and reaction limitation. Sometimes the main one is the mass transfer, how to get the product into the liquid. That's what usually affect the system. Then after that, we'll look at a binary distillation column, how to model a binary distillation column. Actually, if you are good at binary distillation column, it becomes easy to do multi-component distillation column. It's the same thing. It's just that now we try to add some few assumptions just to limit it a little bit. So let's take the first one. Now, there are some reactors that have mass transfer and also um, weight reaction limitation in them. You have a chemical reaction limitation, mass transfer. Like I said, let's assume that you have a bubble of liquid here. Then you have gas. Now, when this one meets this, the gas must dissolve into this, which is due to what? The mass transfer, because you have a mass of gas being dissolved in the mass of the liquid. When it dissolves here, the two will react, form a product. So you see that there's a reaction, then also there's a transfer. Now, if this one is not able to enter here very well, then the reaction will be affected. So sometimes you might see that your reaction is not working well, and you think the reaction is slow. No, what's happening is that there's no an effective transfer of your reactants into the other one to ensure the reaction. So it will limit the whole process. If there is also a good transfer, there could also be a problem of what reaction limitation. We are focusing more on the what's the name? The mass transfer. You get it? So for example, if you have a nice room and you have a good cinema, see that are familiar with the cinema settings. When you go with maybe a nice lady in the cinema and watching the cinema, sometimes by virtue of the law of attraction, there's what mass transfer collusion between the two bodies together with time whilst you are watching the movie. And it depends on the type of personality you are. That will define the kind of transfer that will occur. So the same way in the reactors, depending on the affinity of the molecules. So if it is gas and liquid, on the affinity of the liquid of the gas to the liquid, it tells you how much the transfer will take place or how much the reaction in the. We are saying that mass transfer, because of this, mass transfer becomes a limitation. So, like this scenario I was giving you, if there's resistance from one part and there's no collision, no reaction takes place, everybody will finish watching them will be fine movie, no reaction. But in our case, we want to form product, we want reactions. Okay, very well. So you realize that mass transfer is the biggest limitation in most reactors that has a mass transfer occurring in them. If you're not able to initiate a good mass transfer, then it has a problem. You realize that system will be affected. Your products will be limited. You will not get very good products. Okay, so let's look at how to model such a system and see the number of equations we need to represent such an equation. Now, with this, you remember we talked about constitutive equation. So we have to go back to mass transfer and apply mass transfer equations to the system. If there's additional heat addition into the system, then we have to apply heat transfer and borrow some of the equations there. And also, you will need to use thermodynamic equations as constitutive equations. Yes. Let's look at it, how the reactor looks like. So this is a general reactor, an example of what we call a gas liquid bubble reactor. Now, what happens is that you have a liquid fed into the system through here. Then you have the gas, with the gas here at the bottom. The gas is sprayed to pass through the liquid, so it forms bubbles in the reactor. And these bubbles here, when they form, there's a reaction between the gas and the liquid to form a product, which is collected over here. But sometimes you have some of the gas not reacting. The unreacted gas, we collect it on top here. Don't collect this, it will have a pressure buildup in your system and it will affect your system. Or if you don't collect this out, what you have is what you don't have a continuous system. You have what we call a semi-batch. The gas is not going out, only the liquid that is coming in, and this kind of semi-batch system. The problem we have now is how do this gas pass through this, ensure a good transfer. And if you remember, the reaction to take place, the gas must first dissolve the liquid, and that's a mass transfer behavior. So we have an example of a bubble here, explain the mass transfer between the gas and the liquid. Look at this. This is the liquid, okay? And this is what we call the liquid form, this gap here. This is what must be overcome, get the gas into the liquid phase. So the gas, what we have here is what we call the gas liquid interface. That's what we have here. The distance between this, which we call the liquid form, I will call the metastable stage. At that stage, system is not very stable. Don't know whether you have more or less. So the gas here is what Ca star. It must overcome this into this system to have Ca. And is this Ca we want to predict? We want to know how much gas has been dissolved in the liquid. That's what we want to predict. We need an equation that will let us know the amount of gas in this. We know this. It means that we know that we can tell at each point in time how much gas is in the liquid phase, how much gas is coming out. Then we can now understand how this whole system behaves. That's what we're trying to model. So let's look at how to model this system. So like we do, our usual practice, after understanding the system, the next thing is to take the assumption that is needed for the system to operate. So let's type the reactor a little bit further. We write the assumption. So we are assuming that you have reactant A, which is it's liquid, it's the gas, right? Yeah. Which flows into the reactor, meet up with another reactant, which is B. They react to form a product C. And we are assuming a first order reaction in them. So first order reaction, the rate is going to be K, concentration of A, of B, first order. This is what we have. So we apply this. And it is saying that reactant A must dissolve into the liquid, which is true. If you have poor dissolution, the reaction will be limited. And if the rate of mass of A in the liquid is low, the concentration of A in the liquid is low, means use up much. And this is what we call mass transfer heating system. Let's look at how to. So for simplicity, assume what an isothermal constant hold up, constant pressure, and constant density condition. Okay. We're also assuming what a perfectly mixed liquid, which means that the liquid coming in is perfectly mixed. So there's no what's it? There's no limitation to the absorption or the dissolution of the gas in particular point of the system, which means that any amount of liquid that comes in has the equal ability to or to absorb the gas that is being the reactor. All right. And we are saying that for each bubble, there is an area which is A empty, which is what the mass transfer area for the system that could react with the feed into the system. All right. So with this, we can write our equation very easily. More assumptions that we need to state, or more equations. Here we have to apply mass transfer. So they're saying that NA, which is what? Which is the mass flux, right? NA equal to what? The mass transfer coefficient KL times the concentration gradient. Remember, the first the here is going to be this is the concentration gradient. This amount here, but here is more, and this will be less minus this times the mass transfer coefficient. I'll give you the mass flux or the transfer flux into the bubble. So let's go ahead and define other things. And then also, we assume what? The vapor phase dynamics are very fast and that any unreacted gas is vented at the top of the reactor. That's this part. Here. So any unreacted gas comes out from here. And we are saying that this VF here is equal to FA minus AMT and AMA all over here. Here. Oh, what is FA? Look at it. FA is this, right? So what we are trying to say is that the amount of V here, this one, this value here, is equal to the input gas. This one, that's FA. We put FA here Do you get it? We have Fa here at a certain density A, and that is equal to the amount that has been absorbed or dissolved in the gas. That's the second term. The unreacted gas, like you see here, the unreacted gas, which is this one, equal to the amount of gas we put into the system minus the amount of gas that has been dissolved in the liquid. The remaining one becomes what has not been reacted. That's what we want to take. Because this is the mass transfer area, this is the mass flux, this is the molar mass. It's used to cancel the moles, and you balance the equation. Then this gives you the amount of gas inside the liquid phase. Then the remaining one is the unreacted. That's what you system. All right. So that's the total mass balance. So let's look at the component mass balance of A. The component mass balance of A, like we all know, is what? You're going to have the amount of A, the reactor, should be equal to what? The amount of A that goes into the liquid phase. Okay. Then the amount of A that is inside the output. This is output. Remember, this input is the amount of A that is going to the reactor. So this is the amount of A that will be dissolved in the liquid. This is the amount of A that is coming out in the system. And this is the amount of A that has been depleted due to the reaction that's taking place. You get it? That's the component balance. Then for B is also depleted, right? So you're going to have amount of B equal to the amount of liquid that you have pumped into the system, plus the amount of liquid in the system times the rate of yes. So that's how it's going to be like. Total continuity equation, you're going to have the amount of mass accumulation in the reactor. If it is steady state, this should be equal to 0, being equal to what? This is input. We have two inputs. If you remember, we have the liquid input, which is this one, plus the gas into the mass transfer area, minus the output. So this gives you the you have 5 equations to solve. For the variables is what? This is the mass flux, mass transfer flux. So then we have the constitution of A, of B, the amount of unreacted gas becomes a variable. Then this is the amount you are taking. Then the forcing functions are what? The flow rate of A and B. The amount you flow. If you flow more water, you might have more absorption. Okay. So these are the forcing functions. This system. That's how you model reactor with transfer. It's just accounting for the mass transfer coefficient. All right. So the last equipment we'll look at today is the binary distillation. Now, aside CSTR, which is commonly used in the industry, distillation column is the most popular and frequently used equipment in, especially for separation. And we say that distillation is used in many chemical processes for separation of streams and for purification of final product. In fact, almost most of the processes you end up using the distillation process to separate the products. So it's very common. It's applied in different. Most of them are what multi-component, but we normally make them in terms of binary or pseudo binary. and we use equation. So we try to idealize some of the processes to ensure successful model. So if you remember, we did flash drum, right? So we talked about this continuity equation, which is used to calculate the what's the name? Used to calculate the composition of gases in the system, which is driven by what? The relative volatility, alpha. It's not E. This is right. So let's look at the assumptions in a binary distillation column. We assume that what? We have two components. One is volatile, one is heavy. Our priority is to take away the volatile component. We are also assuming that these two components have a constant relative volatility throughout the whole column. And theoretically, it has 100% tray efficiency. Which means that you have the two components on a tray, you have 100% separation of volatile from the heavy component. So if that is correct, then this equation holds the removal of the volatile component. That is why you are seeing Yn, which means what? Because on each tray, the volatile component comes what? Gas. So its mole fraction is Y, not X. So this is how the equipment looks like. Let's look at how, and we look at how we. This is a binary distillation column. Wow, this is a nice one. Now, what happens is that let's look at the stages, and that will help us to design the model for this. If you look at this very well, we have this part, which is the reflux. We have this part, which is the reboiler end. Then we have here, which we call the top tray. Then we have the first tray. Then we have what we call the third tray. Usually in a distillation column, you don't put the feed at the bottom. You put the feed a little bit. And so we have at least a tray that we use. So the feed tray is always above the first tray in the column. Then you have several trays, which we call the end trays. We are going to write a continuity equation for this reflux area. We're going to write total and then component. When we come to the boiler, we'll write total and component. First tray, we'll write total and component. Tray, total and component. All the trays in our column, we are going to write their total continuity equation. Then they are the same thing. So you see that usually for a distillation, you can have more than 50 equations to solve in order to model it. Like this example, I think we'll have about 47 or 9 equations that you need to solve in order to predict the position of each product at a particular point in time. And that's the goal. And that's the goal. So like the first one, we have our feed here. It is the feed. Comes at a certain composition of what? Z. Which is what? The mole fraction, more volatile one, right? That's here. Then when it comes here, the vapor will travel up to here. So you see there's V here. And this V here, the volatile component there is the N. NT stands for what? The top tray. Then it comes down here to the condenser. Then we have the reflux. Then we pump the reflux back on top to the top tray. You see the reflux. So that's why we have R here. Then we withdraw the distillate. After it is pure, we have the distillate here. Okay, so you see that the reflux here is an addition. Sorry, the vapor here, this one, this V is an addition of what the reflux plus the distillate we have withdrawn. Now going to derive the equation for this, but before that, it's better we look at the atom first and we come to the equation. So let's look at specific assumptions. So the content of the drum is assumed to be perfectly mixed with XT. That's the last part in the drum. Then say that the liquid in the drum is at its what bubble point. It means that once it's at its bubble point, it's ready to ensure perfect or 100% separation, as we said. Then the reflux is pumped back to the top tray, which is called the NT of the column. At the reflux overhead distillate product, and we remove at a certain rate. Then we also neglect any delay time, which is called the dead time in the vapor line, which means that the vapor travels uniformly up the column. It goes straight up, and there's a very good movement of the vapor from the bottom to the top. Then also say that YNT is not equal to what the XT. So the volume, this YNT is what we condense to find what? It's what we condense to get the distillate and then the reflux. So they are not the same. And then we also say that what at the base of the column, the liquid bottom product is removed rate and then we have a vapor reboiler which is generated, and then we put the vapor back into the system. This is to ensure that purify the heavy product also from any lighter components before it goes out. So we do that at both ends. In the reflux, what we are doing is that we want to make sure that there's no heavy component in the lighter component. We want to purify the lighter component by removing all the heavy components. We pump it back. In the reboiler, we are also making sure that there's no lighter component that is accompanying the heavy components. We try to purify that aspect to make sure that we will have pure heavy components at the bottom and pure lighter components on top. Okay. So let's look at how this is done. I think we still have some series of assumptions to make. And we are using a shell and tube reboiler to do that, which means that we try to use steam. So we heat steam, pass it through, and then the heavy component passes through that to gain more momentum and the vapor. Then we also assume that the liquid in the reboiler and the base of the column are perfectly mixed and have the same. The circulation rate through the reboiler is quite high, and this is very good in order to ensure perfect separation of lighter components in the reboiler. Of the vapor leaving the base of the column and entering tray 1 is what? YB. Why? Because it's going to be vapor, so it's going to be YB. And this liquid is in equilibrium with the liquid heavy composition inside the reboiler. Then we also assume that the column contains a total number of NT theoretical trays, and the liquid holdup on each tray, including the downcomer, is MN. Later, you guys will understand downcomer. I think you will do petroleum refining process, so you understand downcomers. Then the liquid on each tray is assumed to be perfectly mixed. The holdup vapor is assumed to be negligible, which means that there's no vapor on the tray. When you get to the tray, the vapor will escape directly. It drops down. And then, although the vapor volume is large, the number of moles is usually very small because the vapor density is so small than the liquid. So this assumes what breakdown, and this ensures high pressure in the column. And we have more assumptions. We also assume that we have an equimolar overflow. And if the molar heat of vaporization of the two components are about the same, so it means that whenever 1 mole of the vapor condenses, similar mole of liquid will be attained. Okay. Then the heat losses of the column and temperature changes of the tray are assumed negligible. Sometimes this is in reality, this is not true, and sometimes you have to add or increase what we call the runabout it's run around or something, the turn around. So sorry, pump around. So pump arounds are you add more crude oil to try to maintain the temperature. Then also we assume that what's the last assumption? It says that this assumption means that vapor in the liquid rate with the stripping, the rectifying section can be constant under steady state. Okay. So it assumes a good separation efficiency on each of the tray, not affected by the temperature changes and heat loss in the system. This will also lead us to the assumption that liquid hold up on each tray constant. So you see that V is equal to V1 is equal to V2 equal to V3 for each of the trays. Then also saying that the liquid flow can be simplified as a Francis Ware formula relationship. So we use this formula to calculate the liquid hold up on each of them. And we are saying that this is the simple formula that can be used to calculate. So this has to do with the tray spacing. It means that the trays are well spaced according to. Then we also assume a simple relationship for liquid hold up and then the liquid rate throughout the system. Finally, we will neglect the dynamics of what the condenser in the root boiler. So any changes, we assume that the root boiler is working perfectly. The condenser is also what's working. But in commercial columns, I mean, the dynamic in these processes must be well. Yes. So now let's go straight into the model. Then like I said, we are going to model the condenser and reflux area. Then we model the root boiler area, model the first tray, model the feed tray, model the top tray. That will add all the equations from this. And let's look at the first one. For the condenser and the reflux, remember, I told you that the mass, the total mass with time will be equal to what? The vapor that is collected minus the reflux minus the distillate. Okay, that will be the remaining amount that will be left, okay, inside the reflux. That's the total continuity equation of the area. Now, for the component, that's the distillate. So it's going to be what? The percentage of this that is remaining. That will be the mole fraction distillate. So you have X distillate minus B here times the fraction of the light component in the vapor that you collected, minus the percentage of light component in the distillate, and then the percentage of light component in the refractant. So this gives you the component analysis of light component in the condenser or reflux. Okay. So when you are done with that, go next to the top tray. Now, for the top tray, interesting things are happening there. You have a tray like this. Okay, it has a liquid on it. And then now look at this. If you remember the top tray, the reflux comes here. You remember that. So there's a reflux coming. So the reflux liquid we are pumping is an input to the top tray. You get it? It's an input to the top tray. Then when this one comes, the liquid here will leave the top tray. There will be a liquid that will leave the top tray. Then there will be vapor. The vapor will come to the top tray. And then there will also be vapor in the top. You see that we have two inputs. This is an input vapor. This is an input liquid. Input liquid. Input liquid. This is an output liquid. This is output vapor. So that's how we do the component analysis for that. But for the total continuity equation on this tree, we're going to say that the amount of mass of the light component, which is NT, on this tree, equal to what? Reflux R minus the liquid that is leaving this tray, LNT. Okay. That is going to be total equation on this tray. But for the equation for the moles of the light component, that you are going to take the percentage of the light component here equal to percentage of the light component in the reflux, that's this place, minus the percentage of the light component that is leaving the tray, that's the one coming down here in the liquid phase. You know, the trace, liquid always flow down the trace. So this is the composition of the liquid tray plus the composition of the vapor phase that's coming to the tray. That's here. Of the light component is that's from NT minus 1. NT minus 1 is the tray below the total, the top one. There's a tray here, and this tray releases vapor this as an input. That is the vapor percentage of the light components, NT minus 1, that is coming on, minus the vapor that is leaving, VYNT. That's what is leaving. You have this as your continuity. Tray. Now, from the aside the top tray, we now have another tray, right? So it's like this, which we call the NT minus 1, because you have this, you have a 1 here, this is NT. So this tray is NT minus 1. The next tray below this is going to be NT minus 2. Each of these tray has liquid coming down, gas coming in. So you see that the liquid that was coming down from the end here will now become the input liquid on the NT minus 1. Then the liquid that is leaving the NT minus 1 will become the input, the NT minus 2. Then the vapor that is leaving the NT minus 2 becomes the input vapor for NT minus 1. The vapor that is leaving here becomes the input for NT of the top one. Okay, so with this, we can write the continuity equation for the NT minus 1, which means that the mass on NT minus 1 with T is equal to the liquid that is coming in. The liquid coming to this tray comes from the top tray, which is NT. So it's going to be liquid NT. And the output is what is leaving, which is liquid NT minus 1. That's the total continuity equation. Then if you want to write the component equation, we will have, means that you want to know the percentage of the volatile component on the NT minus 1 tray. So it's going to be a percentage, which is this one, times the percentage of the volatile component on with time be equal to what is coming in. If you remember, what is coming here is from the NT, the top one, which is NT. So it's going to be liquid NT times the percentage of the lighter component in NT minus the one that is living here on this tray. So it's going to be LNT minus 1 times NT minus 1 in that. But there's vapor coming in here from the bottom, which is NT minus 2. It's going to be vapor NT minus 2. That's the lighter component, right? Minus what is leaving that tray is VY NT minus component balance for the. Then you now do that for the nth tray. So for the nth tray, which means for each of the trays, you are going to have what the liquid that is dropping on it minus the liquid that is, and then the percentage of the lighter component in on that tray is equal to what? The liquid that is coming in, the liquid that is coming in from the top of the tray, percentage of the volatile component minus the liquid leaving in as the vapor coming in minus the liquid. So when you do that, write the same thing for now. So now on the feed tray, remember, it has the similar behavior we have just done. It has an addition of what? Receiving an input, which is coming in. So the amount of light components on this one is going to be what? The percentage of light components in the tray on top brings liquid down to it. That's this one. Times the mole fraction of the lighter component minus the amount of liquid leaving that tray plus this is the vapor that is coming in from the bottom tray. You remember that we said that usually the feed tray is not the first tray. So the first tray will give some amount of vapor to this minus the amount of the lighter component that is leaving that tray, then plus the input vapor. The input vapor. That becomes the component continuity. And you know that Z, we said Z was what? The percentage of the lighter component inside the feed. So when you do that, you now establish that. Then you now write also equation for the first tray. The equation for the first tray will also be very simple. So it's going to be the mass on the tray. That's the total continuity. The mass on the tray is equal to what? The liquid that is coming on from the first tray to this minus the liquid that is leaving the whole system to the room boiler. Okay, so with that, find the percentage of the lighter component. If you want to check the component analysis, it's going to be what? The liquid that is coming to the tray, the percentage of the lighter component in it, the room boiler. Vapor, you remember the room boiler vapor was YB. So that's this one. So this is the vapor that is coming in from the room boiler. Minus the vapor that is going to the. Then if you do this, the last thing, write the continuity. for the what's the name? The road boiler. So for the road boiler, you have the liquid that is leaving the first tray. It's this one. You get it? Minus two things are leaving the road boiler. One is the heavy component, and this is the vapor that comes. So the liquid coming into the road boiler, that's the input, minus the output vapor, the output that becomes the right component mass balance of the heavy component. Going to be the heavy component inside that equipment times what? So the amount coming in. So the liquid coming down here, you look at the percentage of heavy component in it minus the percentage of component in the vapor that is going into the distillation column as flash as vapor from the root boil, then the amount we are removing. When you are done with this, you establish all the equations for it. Then you need two additional equations. This one's here to define the hydraulics. The base, that's the root boiler, and the flash drum, because you pump, right? That's the hydraulics. You pump the liquid from the root boiler back. Then you pump also from the condenser back into the system, which is the root packs. So you need these equations here. Find the hydraulics. So when you add them together, you see that you're going to have what? The trays are what? The tray composition is XN and XY, right? So you have two NT. Then you have two liquid flows. Then you have tray liquid holdup, which is the M, reflux drum composition, reflux drum flow. Then you have reflux drum holdup, phase composition, phase flow, phase holdup. So these are the number of variables you need. When you multiply them, depends on the number of trays. So you're having, let's say, 10 trays in this distillation column. It's going to be 4 times 10 plus 9, which is 9 variables to have in this system. Same way, you're going to have similar number of, and this one you have 47. So 47 equations, you realize that we have 49 variables, 47 equations. So it does not satisfy the phase rule. So the two other hydraulic equations you solve, if you add it to this 49 equations, then you can solve for all the variables using your Python or your MATLAB program. So when you finish, see that the two equations here helps you to complete the in terms of control process. Then you are able to solve the equation. Thank you very much. Any question on these equations so that we can talk about our next class?
I think it's almost the same thing you gave us, right?
No, the assignment I gave you is on batch graph.
Okay. All right.
Yeah. All right. So I don't know. Since you guys say you are going to start the next model yesterday or something, so tomorrow we can just meet. If there are any questions or anything, I think I want to. I think with this one, you can develop all the variables you need in any simulation. And I'm also available. I think you have my email, my contact. If you have any say simulation problem or challenge or like or anything, just we'll work together. So we'll meet tomorrow and then we finalize. Any question?
Okay, sir.
All right then.
But it's not really easy, but we are still following.
Pato, I hope I'll stop here. I will not kill you guys again.
Okay. Thank you very much.
All right. Thank you so much. And guys, tomorrow. Today we've not heard from Amma. Oh, she's having an Easter party.
No, I'm here saying.
Or you do go to work or you had a holiday?
Yeah, I went to work.
Wow, God is blessing you.
Hmm.
All right, guys. So see you and then we can talk anytime.
Okay.
All right. Bye.